If you're just getting into your first stats course, then imagine this with me. Say your school has 5 sections of stats classes, each with about 20 students, who are all given the exact same test. Some students do well, others not so much. As a student yourself, you might wonder how you did, and your teachers might wonder, in general, how the whole school did. Now, if you had a lot of time, you could individually ask each student to describe how they did on the test. And if you had a really good memory to store all of that info in your head all at once, then you'd probably have a good feel for how the school did overall. But do you really want to do that? If it's even possible, it's not particularly practical. And as it turns out, there's typically a better way. Specifically, statistics is about using mathematical tools to analyze and interpret this kind of data. In other words, to answer questions exactly like this. Our example here is specific to student exam performance, which presumably, if you're watching this video, may be relevant to you. But try to think for a moment. There are a whole host of similar styles of questions that might feed your personal curiosity based on whatever interest is personal to you. Maybe you care about which of your favorite basketball players is better at free throws, or where to find affordable housing, or which thumbnail is going to generate more interest on your latest social media post. I'm sure you can come up with many more examples, but the point is that statistics can be a powerful tool to bring insight to all of these kinds of questions. So how can we actually answer them? Well, there are a lot of ways and a ton of different tools within the subject that will allow us to do just that. And we'll certainly explore those over the next few videos. But let's start with getting on the same page with at least a couple of key terms so that we can make sure that we're all speaking the same language. 2 of the first bold words you'll see when you crack open any stats textbook are going to be population and sample. So what do they mean? Well, if we think about our school example, there were 5 stats classes with 20 students each, and we were wondering how the whole school did on the exam. The test scores of the whole school, of the 100 students taking stats, would represent our population. All of the data that we're considering in our question. If we wrote all 100 scores out in a list, that would be our population. A sample would be like the 20 students in your class, or maybe just the scores of you and your 4 closest friends, or maybe even just your score alone. Basically, any smaller part of the whole population, any subset, that would be your sample. Now, your score on its own would represent a sample of size 1, and your class's score would represent a sample of size 20. Now, as you might imagine, looking at your score on its own, that might not be enough to determine how the whole school did on the exam. Presumably, because you're watching this video and practicing a lot and studying very hard, you did fairly well on the exam. And this may or may not necessarily reflect the scores of the students who maybe didn't put in the same effort. On the other hand, looking at your class of 20, that might help us get a little bit of a better sense, because naturally in a class of 20, there's going to be a much wider collection of students having given a much wider collection of efforts and thus earning a wider collection of scores. So right off the bat, we can get a sense that a larger sample is going to help us get a better representation of the whole population. Now, this is something that we'll explore in much more detail in future videos, but it's worth getting a sense of, getting a feel for as we learn these new terms of population and sample. But thinking a little bit further about this particular example here, there's a ton of other questions that we might ask. We might think, well, what was the highest score? Or maybe what was the least highest score of the whole school? Or what's the highest score of just our class alone? These things have names too. Specifically, the highest score of the whole school, that would be called a parameter, or some number that describes the population as a whole. The highest score of our class specifically, that would be called a statistic, or some number that describes the sample. So in other words, parameters describe populations and statistics describe samples. And if you're open to getting a little bit cheesy, these even come with a cute alliteration that will help you remember, because parameters portray populations and statistics summarize samples. Maybe that's a bit too much. Anyways, let's consider another example. Let's say we were wondering how many kids in the US had smartphones. We could think about this question from a statistical perspective. Thinking first about the terms that we just learned, you might be able to recognize in this case that our population would be all of the kids in the country, all of the kids in the US. Now, similar to our school example, it's going to be pretty difficult to go through and ask every single one of those kids whether they do or do not own a smartphone. If we wanted to get a sense of the bigger picture, we're instead going to need to take a sample. So what does that look like? Maybe we pick a dozen schools randomly across the country and ask each of their students. Say this totaled to asking 2,500 students or something. These 2,500 kids, those would be a sample of the full population. Now I want you to ask yourself, in this case, what would be an example of a parameter and what would be an example of a statistic? This one might be a little bit more tricky at first though, because unlike our exam question, there isn't necessarily an exam score directly associated with having a smartphone or not, right? It's not really a number, right? Like you kind of just either you own one or you don't. It's a very yes or no. Now, that doesn't mean that there are no parameters or no statistics or no way that we can use analytical thinking to answer these questions though. It just means we have to make a distinction. And this is where we can get into one of the second big ideas that typically opens up the beginning of a stats book. Because broadly speaking, there are two types of data. The first, like our exam scores, they have a number attached to them. Measurements, counts, percentages, etc. We call these quantitative data, right? Because they're based on quantities. The other, like the yes or no smartphone example, would be called qualitative data. Basically anything with non-numeric labels like yes, no. These can be binary, like yes or no, true or false, on or off, but they don't have to be. They could be something like a list of European countries, like Spain, France, and Italy. A list of colors, like red, blue, green, etc. A list of occupations, like entrepreneur, nurse, teacher, and so on. And so qualitative versus quantitative, that's one of the key frameworks which we can understand different types of data. Beyond just those two, there's a few additional, more nuanced ways we can categorize data further as well. Quantitative data specifically can be broken up into discrete or continuous data. For example, if you asked how many people passed the exam, this would be a discrete variable because you can't break it up, like you can't have half a person or 2/3 of a person who passed the test. It's just like, well, you had 5 people or you had 12 people or you had 30 people. We call that discrete. On the other hand, if you asked, what is the temperature outside today? That would be a continuous variable because you can keep getting more and more precise, at least relative to how sophisticated your thermometer is, right? Like 75 degrees versus 75.5 versus 75.55 or 75.55555, and so on and so on. Qualitative data can be further categorized too into what we call nominal and ordinal data. Nominal, like nom, a root for name, literally just meaning variables that can be labeled or named, but have no other mathematical interpretation. This could be like the countries Spain, France, and Italy. They're labeled or named, but there's no inherent structure otherwise. You can't, for instance, subtract Spain from France or get anything meaningful out of Italy plus Spain. And that's what makes these purely nominal. On the other hand, ordinal data, just like the root ord from order, is any qualitative data that has some kind of additional ordered structure. Have you ever taken a survey that asks you questions on a scale of like extremely dissatisfied to extremely satisfied? That would be an example of ordinal data because there is some clear ordering, right? Where extremely satisfied is the highest, and then regularly satisfied, and then neutral, and then dissatisfied, and then extremely satisfied. And it ranks in order like that. That ranking, that ordering, that's what makes a qualitative variable ordinal. Now we can note that while we do have an order, right, extremely satisfied is better than neutral, which is better than extremely dissatisfied, we can't necessarily presume anything in terms of like the difference between them. In other words, though you might be tempted, we wouldn't want to put numeric labels on these, like assign -2 to extremely dissatisfied, 0 to neutral, and 2 to extremely satisfied. You've got to be careful about this. Just because there's an order, it doesn't mean we have any more information about the differences between them. We don't know that the difference between extremely satisfied and satisfied is exactly the same thing between satisfied and neutral. There's nothing inherent about that order that implies the additional structure, so we want to make sure we keep it a qualitative variable only in a case like that. Finally, getting back to our smartphone example, the yes-no aspect can be considered a qualitative variable, but we can also convert it into a quantitative one if, for instance, we consider it as the proportion of kids who own a smartphone. In other words, the ratio of yeses, people who own a smartphone, divided by the total number of people. And this idea brings us to our last distinction, which would be a ratio quantity versus an interval quantity. This one can be a bit tricky, but basically the proportion of kids who own a smartphone, that would be a ratio. First, it is represented by a ratio, but more specifically, there are two properties that indicate a ratio quantity. The first, 50% of kids owning a smartphone would represent twice as many kids as 25%. There's a meaningful multiplicative relationship there. 50% means twice as much as 25. And secondly, 0% would represent no one owning a smartphone. In other words, 0 is always going to equal none. Now, that might seem really obvious when you put it like that, but if we contrast this with a quantity like temperature, where 50 degrees doesn't necessarily mean it's twice as hot as 25 degrees, and 0 degrees doesn't represent no temperature. Temperature would therefore be an interval quantity, not a ratio quantity. So it's important that we make that distinction. Those two properties feel intuitive in context of an example like proportion of students who own smartphones, but when we think about them in contrast to an example like temperature, we can see they don't apply in all cases. And so that's going to be how we distinguish ratio quantities versus interval quantities. Now that you're more familiar with these terms and some of the big picture of statistics, don't be surprised if you start to notice them as you go about your daily life. Data that is quantitative versus qualitative. Qualitative data that can be ordered, or a sampling of a bigger population, and so on and so forth. Hopefully you'll find that it allows you to think about the world a little bit more critically, and hopefully you found this video helpful in general. As always, let me know if you have any questions, and have a great rest of your day.